Ma'am, can you hear me, Durga Devi, ma'am?
Jasmine, ma'am.
Ma'am, can you hear me?
Yes, ma'am. We can hear you, ma'am.
Okay, and also you are able to see my screen sharing, right?
Yes, ma'am. We can view your screen, ma'am.
So shall we start, ma'am?
Uh, Ma'am, shall we wait for 2 to 3 minutes, ma'am?
Yeah. Okay.
We can see like participants are still joining, yet to join, ma'am.
Mm-hmm.
Hey, ma'am, can we start, ma'am?
Yes, we can start.
Yes, ma'am. We
Yes,
can
ma'am.
start.
Good evening, all. I welcome you to the sixth day of this ATAL online FDP on smart systems and emerging technologies in Industry 4.0. Today, we have the first session on robotics and autonomous systems in smart industries by Dr. K. Sujata, Dean Consultancy and Professor, Department of EEE at Dr. MGR Educational and Research Institute, Chennai. I invite Mrs. V. Hema Malini, Assistant Professor of EC Department, to frame out the profile of Dr. K. Sujata. Please, ma'am.
Thank you, Jasmine, ma'am. Good afternoon, all. It's my great privilege to introduce the speaker of the day, Dr. K. Sujata, Professor, Department of Electrical and Electronics Engineering, Dr. MGR Educational and Research Institute, Chennai. Dr. K. Sujata is an accomplished academician and researcher with over 25 years of teaching experience and 12 years of research expertise in applied electronics and image processing for process control. She holds a BE in Electrical and Electronics Engineering, ME degree in Applied Electronics from Anna University, a PhD in Information and Communication Engineering from Anna University, and is currently pursuing her postdoctoral fellowship in Computer Science Engineering at Lincoln University, Malaysia. She has successfully guided 7 PhD scholars with 8 more under her supervision and has a Scopus H index of 5. Dr. Sujata has published extensively in reputed journals, delivered invited talks in national and international forums, and holds an innovation patent for her work on endometrial cancer detection. She has also developed multiple MOOCs and digital learning modules in digital image processing and related domains. Dr. Sujata has been recognized with several awards, including the Young Researcher Award from Qingdao, China in 2015 and multiple excellence awards in education field. She has served as a session chairperson, keynote speaker, reviewer for top-tier journals like Elsewhere and Springer, and a member of numerous international program committees. Her collaborative engagements include academic exchanges and research collaborations with institutions in China and Malaysia. Known for integrating technology with education, Dr. Sujata's expertise spans artificial intelligence applications, control systems, automation, and digital signal processing. On behalf of Department of ECE, I welcome you, ma'am.
Yeah, thank you, ma'am. Now, very good evening to all the participants. So now let us move on to the session. So I'm going to discuss about how to make the power generation system a smart one. Okay, so that it becomes an autonomous system. So this is the order of my presentation, which I'm going to deal with today. So we all know that in thermal power plants, how the power is generated, right? So in thermal power plants, what is happening? The main fuel used is the coal. So you are going to burn the coal in the furnace, right? So as a result of combustion, heat energy will be produced, and this heat energy will be used to heat the feed water present inside the boiler. And this feed water inside the boiler is also preheated water, and the preheating takes place because of the exchange of heat energy from the exhaust gases. So now, in order to minimize the flue gas emissions, right, you have to have an automated control of the burner that is there in the furnace, so that you can go for an online measurement scheme for measuring the temperature, and also to monitor the various constituents of the flue gas emissions. So when I say various constituents, it means that I am talking about the nitrogen, oxides of nitrogen, oxides of sulfur, carbon dioxide, carbon monoxide, and so on. And also you can monitor the flame temperature. So all this you are trying to do by analyzing the flame color. So all this you are trying to do this by analyzing the flame color. And so what you do is you try to infer the parameters, right? You try to infer the parameters from the flame, that is the brightness value of the flame. So you find out the brightness value of the flame, and this brightness value will depend on the pixels that is available in the flame image. So based on this brightness value, we talk about the combustion characteristics. Okay, we talk about the combustion characteristics. Based on the combustion characteristics, we infer the flue gas emissions and also the flame temperature. So this work will enable you to automate the monitoring of the combustion quality by using image processing techniques and also using an intelligent flame monitoring scheme. So what is the motivation? So the main motivation is I must ensure complete combustion. So how to go about complete combustion? I need to adjust the air fuel ratio, right? So I want to adjust the air to fuel ratio. So when I'm adjusting the air to fuel ratio, normally the nominal value of the air to fuel ratio is 4:1 in a thermal power plant. That is 4 parts of air to 1 part of fuel. Okay, so 4:1. So I must ensure complete combustion by adjusting the air to fuel ratio, and this is done manually. There is no automated system. The air fuel ratio is somewhat slightly, there is a variation in the air to fuel ratio. The process engineer has to give a command to adjust the supply of the fuel and the air. So this is what is happening. And in the case of incomplete combustion, this can be done by looking into the flame color. Actually, the complete combustion and incomplete combustion or partial combustion can be identified by looking into the flame color. Okay. So now I need to monitor the flame color. So when the flame color, when there is a variation in the flame color, right? If it is going to be yellowish, whitish to yellow, right? Whitish yellow, then you can say that the combustion is complete. Somewhat reddish, then you can say that it is a partial combustion. And if there is, if the flame color is blackish, right, then the combustion is going to be an incomplete combustion. The flame appears to be blackish in color because of the presence of the unburnt carbon. So you know the major constituent of the coal is carbon. Okay, 60% of the coal contains carbon, then the calorific value of the coal will be high. Okay, so if the coal is not burnt properly, then the flame color will be black. Okay, and at present they are I mean, at that time they were using only the gas analyzers for measuring the flue gas emissions. Okay, and this gas analyzer will be placed at the exit point. When I say exit point, it means it is placed near the chimney. So when it is placed near the chimney, the gas analyzers are worn out. Why? Because of the cold end corrosion. What do you mean by cold end corrosion? So when the flue gases are leaving the chimney, right? Imagine the temperature of the flue gases will be around 230 degrees centigrade. Okay. Imagine the temperature of the flue gas content will be 230 degrees centigrade. But you take the flame core of the core, or the temperature of the flame core. If you measure the temperature at the flame core, it is somewhere around 1250 degrees centigrade. Okay, there for ensuring complete combustion. But the exit flue gases will have a temperature of nearly 230 degrees centigrade. So you can't allow this flue gas to exit into the atmosphere as such. So it has to be cooled down. So from the cooling tower, they spray water on the flue gas at when it is exiting through the chimney. So when they are spraying the water on the flue gas, what happens is that you have oxides of nitrogen, oxides of sulfur in the flue gas. So now water combines with this oxides of nitrogen and sulfur, forming sulfuric acid, nitric acid, and so on. So now this acid formation will come into contact with the gas analyzer. So when this acid formation comes into contact with the gas analyzer, what happens is that the gas analyzer will be worn out. So this phenomena of the flue gases, that is the sulfur dioxide and nitrogen oxide getting converted to sulfuric acid and nitric acid, is called as cold end corrosion. So the gas analyzers will be subjected to cold end corrosion, which will damage the gas analyzer. And imagine the gas analyzer is a very costly equipment, and without the gas analyzer, there is no possibility there is no possibility for a process engineer to find out what will be the exhaust flue gases in the what will be the amount of various gases in the flue gas, exit flue gas. Okay. So even though the gas analyzers are giving you the instant values of the emissions, it is not economical, because you need to invest a large amount of capital cost for installing this gas analyzer. Okay. And because of all these problems existing, this has motivated to go for the research work, where you are going to incorporate image processing and intelligent algorithms for monitoring the flue gas emissions and combustion quality by processing the flame images. Okay, so the flame images can be processed. Based on the color of the flame image, you will be able to infer what is the quality of combustion, what could be the flame temperature, what will be the flue gas emissions. Okay, so you need not wait till the flue gases are being generated. Okay, so it will be like a feed forward monitoring system. Okay, and you can integrate this system to the DCS for online monitoring. So this is the motivation of this work actually. And coming to the next slide, right? That is based on the literature survey done. People have worked extensively on this area. You see, they are using some soft sensors for measuring the nitrogen oxides and oxygens, etc., by using genetic algorithm and so on. Okay, and they are using some characterization, pattern characterization to give a pattern for the combustion flame, so that they will be able to estimate the combustion quality. Okay, and you see, you also have people are studying the characteristics, that is the flame stability, right? So the flame flicker, it is called as flame flicker. So this flame flicker will vary with respect to the oxygen supply. Okay, if the air fuel ratio is 4:1, the flame will be burning stably. Okay, the flame will be a stable one. But if the oxygen content is less or high, then there will be some oscillations in the flame. So when there is a flame oscillation, the combustion quality will be reduced. So this flame oscillation and flame stability will once again depend on the coal quality which you are giving as input for firing purpose. Okay. Then some people have used a hidden Markov model to identify the combustion quality, and they are using some three-dimensional visualization patterns. Okay, using the back projection method, they are trying to reconstruct the 3D model of the flame, and from that they are finding out the luminosity, and they are trying to infer the combustion quality also. Similarly, you have uh, people using principal component analysis to determine the combustion quality index from the flame image. So principal component index can be used for either reducing the features, and you can use any other method for you can use a hybrid system of neural network for classifying the quality of combustion, right? And like in the last paper, if you see, they are using a smart sensor. Okay, they are using a smart sensor system for combustion quality control using the principal component analysis. Okay, so now this is the this is the circuit, boiler circuit, right? So now the coal is coming from the coal yard. Actually, the coal which is deposited in the coal yard is uneven lumps. It's in the form of uneven lumps. So you have to powder the coal and use the pulverized mixture for combustion process. So when I say pulverized mixture, that means the coal is transported from the coal yard through the conveyor belt. It is reaching the pulverizer, right? So when it is reaching the pulverizer, the coal is grinded into fine powder. So before the pulverizer, you have grinding mills. Okay, you have grinding mills. So this grinding mills will be grinding the uneven lumps of coal into fine powder. Right now, this coal dust, since the coal is taken from the Earth's surface, you have some metallic components also there in the coal. So you have to remove. You require only pure coal dust for combustion in the furnace. So what you do is you pass the pulverized coal into the, so you pass the powdered coal into the pulverizer, right? So this pulverizer contains electrostatic precipitator, wherein the magnetic field in the precipitator will be attracting all the iron particles, and the coal dust, which is a non-magnetic material, will be left down. Okay, now this coal dust will be mixed with air and it will be evenly spread out on the floor of the furnace. And once again, what is the advantage of using this powdered coal, pulverized coal? It will be evenly spread out on the surface of the furnace so that you can have a even even combustion. That is, you can have a complete combustion. If you are using lumps of coal, directly dump the lump of coal into the burner, what will happen? The required amount of calorific value will not be attained. Okay, so burning of uneven coal lumps will take longer time. But if you use a pulverized coal mixture, what happens? The by a burning process takes place. The firing process is very easy actually, right? So you are the combustion is actually defined as a process of combining the burning the fuel in the presence of oxygen. So you have to mix the coal, with the air and you have to supply it to the furnace. And in the furnace, you can set the firing. Okay. So initially the firing has to be done using the heavy oil and subsequently the firing will be taken over by the coal. So once the coal is being burnt completely, what happens? Lot of heat energy will be generated. The preheated water which is present inside the boiler will be heated up by the heat energy generated by burning this coal. So the water inside the boiler gets converted to superheated steam. Okay, so the steam temperature will be around 530 degrees centigrade. Okay, now this steam will be moving into the this steam will be used for driving the turbine coupled to the coupled to the generator. Okay, so the superheated steam will be driving the turbine. So the turbine is the prime mover which will serve mechanical energy as input to the generator, and the generator starts generating the power, right? So this monitoring, by placing cameras, you can monitor the quality of combustion in the furnace level itself, ensuring complete combustion, so that you can minimize the flue gas emissions. So this is the chemistry behind the combustion, as you know. Now I'm mixing air with the coal, right? When I'm fuel and air are mixed. Fuel contains carbon, right? Sulfur, nitrogen, all this is there, and you have oxygen and nitrogen in air. So now this air is combining with the fuel and it is being burnt. So when it is burnt, the output is the heat energy being released. Okay. Oxygen will combine with carbon, okay, and hydrogen, forming carbon dioxide, carbon monoxide, hydrogen, and nitrogen, sulfur, all will combine with oxygen, forming oxides of nitrogen and oxides of sulfur. Okay, so this is the chemistry behind the formation of the flue gases. So this flue gas is to be minimized by looking into the flame color. Okay, so that we can ensure complete combustion. This is how we are trying to automate the industrial process, and we are trying to provide a smart technology for minimizing the flue gas emissions and ensuring complete combustion to have a maximum power generation. So actually, for doing this project, we have approached Neyveli Lignite Corporation. And if you see the specifications in Neyveli Lignite Corporation, they have given the technical specification. Okay, the boiler capacity is around 690 tons per hour, and the fuel used will be heavy oil and lignite. Okay, so there are totally 6 mills which are grinding the coal. Okay, so actually the firing system that is followed will be called as the tangential firing system, and there are 2 units. Each unit is having a capacity of 210 megawatts generation actually. Okay, the superheated steam is nearly 540 degrees centigrade. Okay, superheated steam temperature is 540 degrees centigrade. So totally the number of burners will be 20. Okay. So number of burners will be 20 burners actually. and you are having 3 conveyor belts which are supplying the coal. Okay. So out of this 20 burners, 12 burners are for lignite. When I say lignite, it means coal. And the remaining 8 burners will be supplying the oil for initial firing. So totally 6 mills are there. Okay. So the startup fuel used will be the heavy oil, which is the light diesel oil. Okay. Now this is the tangential firing system that is followed in the boiler. So when you take the tangential firing system, the boiler, the entire height of the boiler at Neyveli Lignite Corporation is nearly 80 meters or 90 meters, right? And the entire firing process will be completed. Okay, the entire firing process will be over at the 19th meter of the boiler and the 21st meter of the boiler. So at 2 levels, I told you 6 mills are there. You can see the 6 mills A, B, C, D, E. Okay, so A, B, C, D, and E. These are the 6 mills. Okay, so this 6 mills are placed tangentially. Okay, then you have OB is the oil burner, LB is the lignite burner. Okay, then you have the BFD, burner flame detector. Okay, so you have one flame detector here, and you have the entry point for the lignite and oil. Okay, then you can have additional air firing, that is AAF. Okay, additional air firing can be done to this point. So like this, you have like this, in the tangential manner, the system is arranged. So through the lignite burner, you will be supplying the lignite, powdered lignite. Through the oil burner, you will supply the heavy oil for initial firing. Okay. And the burner flame detector will be capturing the flame that is present in the furnace, and it will be displaying the flame on the CCTV available at the control room. So this kind of firing takes place at 2 levels, that is the 17th, 19th meter and the 21st meter of the boiler. Okay. Now, for monitoring the flame inside the boiler, they are fixing infrared cameras, that is your burner flame detector. Okay. So it is present at the 19th meter and the 21st meter, and it is being fixed to the walls of the boiler. Okay. And this infrared camera is perfectly cooled by a cooling system. It is placed inside a jacket. Inside the jacket, cooling water is circulated because the boiler temperature is very high. Actually, the flame temperature is very high, nearly 1250 degrees centigrade. So the camera will be affected by that. So what you need to do is you need to cool the camera. For cooling the camera, you provide a jacket outside the camera by which the cooling water is circulated, and you can change the orientation of the camera by using some mechanism. Okay, there is a motor you can use, and this motor will adjust the orientation of the camera. So currently, before this research, they were only using they were only using this camera for detecting the presence or absence of the flame. Okay. So only if a flame is there or not. Why they are using this system to detect the presence or absence of the flame is that because you can't keep loading the furnace of the boiler without knowing the status of the flame. If you keep on load the furnace of the boiler without knowing the status of the flame, then the boiler will explode. So what is the maximum capacity that you can load the furnace, boiler furnace? Is that 640 tons per day. Okay, that is the limit you can load the furnace of the boiler per day. So you can't go beyond that. Sometimes there won't be flame. Even you try to light up the boiler, even you try to light up the furnace, there won't be fire, and you think that the coal is, the fuel is insufficient, and you try to inject more of the fuel. But when you do so, it will cause explosion of the boiler. So to avoid this scenario, they have kept this infrared camera to detect the presence or absence of the flame. As a part of the research work, what we have done is, instead of using this flame to find out whether the flame, I mean, to find out whether flame is present or absent inside the furnace, we also try to infer the combustion quality and the flue gas emissions from the flame color. Okay, so for data gathering, you must be interacting with the trained personnel there so that you can offer an required control action uh, with respect to the condition pertaining, I mean, existing there. So you see what is the flame characteristics. The color of the flame is going to be whitish yellow or orange color. The temperature at the core of the fireball is nearly 1100 to 1250 degrees centigrade. The coal input is somewhere around 190 tons per hour for a 210 megawatts. The 210 megawatts is the capacity of the is the capacity generation for one thermal power plant, one unit. Okay, and the calorific value that you are able to achieve is 2350 kilocalories per kg, and the air fuel ratio maintained will be 4:1. So the existing setup, you see the infrared cameras are placed in the tangential manner to capture the flame. This infrared cameras are taking the video of the flame and sending it to the control room, whereby the process engineer will say whether the flame is there or not, and based on that they will be detecting, they will be trying to say whether the flame is present or absent. So based on that, they will say the flame is present or absent. Okay. You can adjust the orientation of the camera using the servo motor mechanism, and the entire camera is cooled by circulating water through the cooling jacket, and whatever flame images are captured will be sent to the CRT monitor in the control room. But now what we are going to do is, whatever video is being captured on the CRT monitor, that has to be transferred to the PC, okay, that is your personal computer or laptop, and in the laptop you can have your intelligent algorithms. You can process the flame images, and based on that you can give a you can say what is the quality of combustion and what will be the flue gas emissions. You can predict the flue gas emissions by looking into the color of the flame. So this is the methodology that is being adopted. So we are capturing the flame images, right? That is, the flame video is captured actually. So the flame video has to be converted into flame images. So you are using a frame grabber to extract the image, flame images, and the flame images are pre-processed. Suppose any noise is there, it has to be pre-processed. The noise to be removed actually. Okay, the noise is to be removed, and after the noise removal, what you do is you try to extract the features from the flame image and give it to the classifier. Probably the classifier is an intelligent classifier, an AI which adopts some method of AI, right? So now this when the features that is given to the classifier, suppose you are extracting 100 features, you can give all the 100 features to the classifier. So it will increase the computational complexity. So what you can do is, during the training process, after extracting the features, you can go for feature selection. Which are the features which will enable the classifier to perform well? So those features alone can be given as input to the classifier. So that your classifier efficiency increases. Okay. So this is the general block diagram behind your behind implementing the AI algorithms for flame monitoring. So now what I have done is I have implemented the radial basis function network, back propagation algorithm, all this. So I am reading the flame images. From that, features are extracted. For extracting the features, I'm using Fisher linear discriminant analysis. Okay. By using the FLD, I am trying to reduce the feature set. Okay. The reduced feature set is used for training the radial basis function network. Okay, so the output of the radial basis function network will be compared with the threshold. If it is within the limits, if the variation is within the limits, then you can maintain the existing air fuel ratio, saying that the quality of combustion is complete. Okay, in case if you are if this air fuel ratio is not within the limits, then you have to go for adjusting the air to fuel ratio. At the same time, when you are comparing the threshold, you can also go for measuring the flue gas emissions and the temperature, which will say that whether the combustion is complete or not. So what is the steps that you need to follow? You have to collect the flame images. So we have taken the real-time flame images from Neyveli Lignite Corporation. Then we are going to adapt some pre-processing methods. Actually, the image which we got is not a square image, so we go for square image extraction. Then we followed noise removal. Then also edge detection and histogram analysis was carried out. Then some features like area, average intensity, orientation, centered, etc. were extracted. And then we tried with the classification schemes, both intelligent, that is AI schemes, as well as the conventional schemes. And we try to predict the combustion quality and the flue gas emissions. So these are the flame images pertaining to the three categories. That is, the class 1 corresponds to the complete combustion category. The class 2 corresponds to partial combustion category, and the class 3 corresponds to incomplete combustion category. So in the incomplete combustion category, you can see that the flame color is black. Why? Because of the presence of the unburnt carbon in the because of the presence of unburnt carbon, the color of the flame is black. You see, for complete combustion, it is yellowish and whitish, right? But partial combustion, it is somewhat reddish. Okay. So correspondingly, by capturing the flame images under these three categories, the flue gas emissions will be noted down by the measurements from the gas analyzer. Okay. And this will be formed as a table, lookup table. Okay. Now, from the flame images, so correspondingly, we have captured the values of the flue gas emissions, NOx, CO, CO2, flame temperature, all this with the air fuel ratio. Okay. And at that time, what is the steam temperature also was measured. Okay. So with this table and the flame images, we start proceeding with our work. So the flame images, whichever is captured from the furnace of the boiler, is pertaining to three different combustion conditions. And the size of the original image, which is taken, is 47 cross 35. And we have gone in for square image extraction, that is 30 cross 30. This was done, which 30 cross 30 to be used. For that, an histogram analysis was done to find out which 30 cross 30 of portion of the image can be used. And if any noise is there, you can use median filtering to remove the noise. Okay. And edge detection also was done for all the three groups of images. So class 1, class 2, class 3. Class 1 corresponds to complete combustion, class 2 corresponds to partial, and class 3 for incomplete. So you see the majority of the flame is whitish or yellowish in class 1. Okay. In class 2, nearly 70% is blackish, right? And in class 3, almost 95 to 97% it is fully black. And we have tested the various filtering techniques. We used variance filter, minimum filter, mean filter, median filter. And out of all the filters, we found that the median filter was able to give the peak signal to noise ratio at an optimum range of 63 dBs. Okay. Now we have done the combustion, histogram analysis to find out the range, minimum value and maximum value of the pixel range. In complete combustion category, you see the minimum pixel range itself is 120. Intensity value is 120. The maximum intensity value is 255. Okay. And in the partial combustion category, you see the minimum intensity value is 31, maximum is 255. Okay, so the number of pixels corresponding to 255, the count of the number of pixels corresponding to 255 will be less. But in the case of complete combustion category, the number of pixels corresponding to the intensity of 255 will be many in number. Okay. So like see, if you take the mode for 255, it is 67,368. But whereas for the partial combustion, it is only 60,934. Similarly, you go for the partial combustion towards 255. Towards the intensity of 255, there are no pixels at all, right? So the minimum value is 0 and the maximum value of the intensity itself is only 75. And you see only the mode for the 75. The mode is computed only for the intensity value 75, right? So the pixel values in the range of 75 is having a mode of 50,367. So now surface plot has been carried out. From the surface plot, we are able to find out that the maximum portion of the surface is towards 255 for complete combustion category. And here for partial combustion category, the entire surface is somewhere in the range of middle range of nearly somewhere 160, 170 and so on. And for incomplete combustion, the entire surface is getting completed by in the range of 0 to 75. Now we can go for computing the features. So we are taking the average intensity value, area of the high temperature flame. So which portion of the flame is having high temperature, that area alone is considered. Then centroid of the flame about the x direction and centroid of the flame about y direction, orientation. And also we are taking the discriminant vectors from the FLD, that is the Fisher linear discriminant analysis. Discriminant vectors are taken and given as the features for training the classifier. So this is the flow chart which is followed. So we have collected almost 51 images pertaining to 3 categories. We computed the average intensity. Okay. Then after computing, for computing the average intensity, you have to first find out the average of the gray level of the pixels in the flame. Then you have to apply the first threshold value. You find the brightness of the flame. Then after computing the brightness of the entire flame, you try to compute the brightness of the high temperature region in the flame. So for that, you find out what is the average gray level of all the pixels, and you have to divide that value by the second value of the threshold. Then you compute what is the area of the high temperature flame. So you find the summation of the brightness of all the pixels minus the threshold to get the area of the high temperature flame. Then you find the rate area of high temperature flame using this formula, and you can stop the process of the feature extraction. So once feature extraction is done, you go for FLD because you want the discriminant vectors from the FLD. So in FLD, for computing the FLD, what you do, you read all the 51 images. You have to find the eigenvectors, okay, and you have to locate the diagonal values which corresponds to very high values. Then you are finding the class mean. You are finding the class mean. That is when I say you are having 3 classes, class 1, class 2, class 3. For each class, you are finding the mean value. Then you are finding the global mean. That is one common mean for all these 3 classes. Then you try to find the within class mean. That is within class mean means what is the mean within the class 1, what is the mean within the class 2, what is the mean within the class 3. So when I say class 1, class 2, class 3, it means it corresponds to complete combustion, incomplete combustion, and partial combustion. Okay. Then from this, after computing all these means, you compute the discriminant vectors phi1 and phi2, which will be serving as 2 features for your 2 more features apart from the average intensity, high temperature flame, centroid X, centroid Y, orientation. Apart from that, you add two discriminant vectors which is obtained from this FLD analysis, and this will be given as the input to the classifier. Now, when you are doing the FLD analysis, you can see that you from the FLD analysis is also done to find whether any overlapping between the images are there, because when the flame is burning, the transition will be from complete to partial and partial to incomplete, right? When that is the case, during the capturing of images, some partial images would have been mixed up with the complete combustion category and incomplete combustion category. If that is the case, you have to eliminate all that, then only your classification efficiency will improve. So for that, we have computed the centers for class 1, class 2, class 3 from FLD analysis to see that any overlapping between them is there. But when you have carried out the when you have carried out the computation for the centers using FLD analysis, that is actually you see the size of the image is 47 cross 35, right? And in that you are only taking 30 cross 30. So you have tried this you have tried this for various 30 cross 30 combinations, right? You have tried this for various 30 cross 30 combinations and computed the centers for class 1, class 2, class 3 using the FLD analysis. And in all the cases, you found that there is a distinct separation between the class 1, class 2, class 3 images, which means that which states that you can take any 30 cross 30 size of the image for further analysis. So now the image which you are capturing, the flame image which you are capturing is a color image actually. So you have to do the analysis in the three planes. A color image, it will have intensity in R plane, G plane, B plane. All this put together constitutes a pixel value, right? So in which plane you can go, you can do the analysis. So from these three figures, you can see that in the R plane, if I do the analysis, it will be efficient. Why? Because see, this group 3 is grouped together. Okay, then group 1 is grouped together and group 2 is also grouped together, except only two images. Okay, two images, all the other things are grouped. But in this case, sorry, no, in this case, you see G plane. Okay, G plane also, you see, it is also somewhat efficient. All the group 3 images are together, group 2 images are together, and group 1 images are together. But B plane is not suitable. So you can do your analysis either by combining the intensity values in R plane and G plane, or you can separately take the intensity values in R and G plane and do the further processing. So by extracting the features, we are going in for the conventional classification, that is the Euclidean distance classifier we have tried first. When you are using Euclidean distance classifier, you see the number of misclassifications was very high. That too in the third category, which corresponds to your incomplete combustion. The second category, your partial combustion, the number of misclassifications are very high, 17 and 8. So our aim is to predict the incomplete combustion and the partial combustion, and you have to offer the required control action. So by using the Euclidean distance classifier, the classification is not up to the mark. The misclassifications are very high in number. So we move on. This makes us move on to the intelligent classifier techniques. Okay. So take the Fisher linear discriminant analysis also. In this case also, you see three images are getting mixed up. Okay. That is, in category 1, one image is misclassified, and in the category 2, two images. That is, category 1 is complete combustion, category 2 is partial combustion. So three images are misclassified, and that is why we are using the discriminant vectors of the FLD analysis as two features for training your intelligent classifiers. Okay, so this discriminant vectors are dependent on the within class mean and between class mean and so on. Okay, so now we are proposing the feed forward network, that is the radial basis function network we are using first. So we have taken 7 nodes in the input layer with 48 nodes in the hidden layer and 6 nodes in the output layer. Okay, number of training patterns we have used was 51. And during the training process, the mean squared error of 0.033 was achieved. And we are using Gaussian function as the activation function in the hidden layer and a linear activation function in the output layer, right? So 7 features were used as input to the RBF, right? And what are the 7 features? Area, average intensity, area through the equation, that is the high temperature flame we computed, no? Centroid X, centroid Y, the rate area of high temperature flame, and orientation. These are the 7 features which we have taken. Okay. So based on this 7 features, we have computed what is the efficiency of the RBF. And we have also added 2 more features, that is phi1 and phi2 from your FLD. And along with this 7, this 2 features, phi1 and phi2 was put together, and totally 9 features were used for training the RBF. And we try to make a comparison between the RBF and FLD RBF to prove which one is highly efficient. Okay. So now these are the various outputs for the FLD RBF for corresponding to the flame temperature, corresponding to the CO emissions, NOx, carbon dioxide emissions, and so on. You see only 2 images are being misclassified. Okay, 2 images are being misclassified in the class 1, that is the complete combustion category, right? So this corresponds to the air supply, sulfur dioxide, and then coming to the combustion quality and so on. The 2 images only were misclassified in the first class. When you combined the feature from FLD along with the original feature set, and you trained using RBF, that is your FLD RBF, only 2 images are misclassified. But when you are using 7 features for the classifying for the classifier to classify the RBF, you see class 3 many images are misclassified. What is class 3? Incomplete combustion. So in incomplete combustion category, which is the crucial one, many images are misclassified. Okay. So what we try to do is we have to improve the classification efficiency of the RBF. So we added the discriminant features from FLD along with the conventional 7 features to improve the classification efficiency of the RBF, which was discussed in the previous slides. So this is the comparative analysis that is made, Euclidean distance classifier, FLD, RBF, then your FLD plus RBF. You see the maximum number of images are being classified and when you are using FLD RBF. Okay. And yeah, also the performance measures like precision, recall, precision and recall was the maximum, okay, using your FLD RBF, right? So that's what this made us to go in for analyzing the color of the flame image and automating the entire system to identify the combustion quality and minimize the flue gas emissions. So here we try to propose an indigenous technique for monitoring the flame color, and we proposed a system to minimize the flue gas emissions, and we are trying to save the gas analyzers from the cold end corrosion. So you can do this measurement of flue gas emissions in an online manner by using these intelligent algorithms, and you are using a feed forward control strategy. So in feed forward control strategy, you can minimize the time for getting the measurements, and based on the flame color, you can adjust the air fuel ratio to ensure complete combustion. Okay. And this is also coming under a class of inferential scheme. So you are trying to infer what is the combustion quality from the flue gas color. So you are having a ratio control, you are controlling the air to fuel ratio. So thereby looking into the flame color, you are offering a ratio control scheme. You are offering an inferential scheme because you are trying to infer the value of the combustion quality, whether it is complete or incomplete or partial. then you are offering a feed forward control by looking into the flame color itself. You are adjusting the air fuel ratio to ensure complete combustion and minimize the flue gas emissions. So you can't use your gas analyzers because of cold and corrosion, because they are very expensive. So if you propose intelligent algorithms and embed these algorithms in DCS, you can go for online monitoring of the combustion quality, where you can make the conventional power plant, automate the conventional power plant, or transform the conventional power plant to a smart power generating system. Okay, and you can use this results for dynamic adjustment of the air fuel ratio. Okay, so you require the flame images, okay, for three different categories, and I mean, you can also extend the work by including some intermediate combustion conditions like less partial, highly partial, less incomplete, highly incomplete, and so on. And for this, you so that you can even increase the classification efficiency. So real-time integration is possible when you embed all these algorithms to DCS, and you can monitor, you can do the online monitoring. Instead of doing a manual adjustment, you can do an online monitoring from the control room to provide a cost-effective solution for minimizing the flue gas emissions. Actually, this work was supported by engineers from Neyveli at that time, Thiru Gautaman and Ramakrishnan sir and Shaktivel sir. Ramakrishnan sir played a key role in for capturing all the data, and they have extended their valuable support for gathering the data for us. So these are the references which we have followed. Okay, so this is one part of the research. Then I would also try to discuss the next one, because I have to continue up to 3:30. Yeah. So I will go for the second application. I will share another PPT. Wherein I will be monitoring the quality of the steel sheets. Yeah. So I'm using a smart system for automating the steel processing factory to detect the defects on the surface during the processing of the steel sheets. So I will be discussing in this order actually. So if you see, I'm using deep learning based approach for detecting the flaws on the surface of the steel during the manufacturing process. You know, manufacturing of steel sheets is very highly tedious process, is it not? Why? Because you need to, you need to have a, yes, you need to have, during the processing of steel sheets, the temperature is very high. You can't go and touch the steel sheet as such. Okay, so also you can have a camera to capture the images. You can capture the video during the fabrication of the steel sheets. So when you are capturing the video, the images which are obtained will be a low resolution image, and from that low resolution image you need to infer the flaws that are appearing on the surface of the steel sheets during the manufacturing process. And for this we have used an optimized cascaded CAFnet region network uh, for classifying for detecting the defects. Okay. And we are using also we are using some convolutional neural networks with electric fish optimization approach for detecting the faults in the steel sheets. Okay. And finally, we have evaluated the performance of the proposed model using the defect detection accuracy, okay, and mean absolute error, and so on. So when you go for the introduction, so when you go for the introduction, you see there are a lot of there are a lot of imperfections. Okay, they include scratches, holes, scars. Okay, and can you see my screen actually?
Yes, ma'am. Before it was visible. Now it's not visible now.
Okay, now.
Yes, ma'am. It's visible.
So,
Visible.
so there are a lot of imperfections like scratches, holes, scars, and so on. So totally, we have taken 4 defects, okay, for making the study. So when you are able to identify this kind of defects during the processing itself, you can go for producing high quality steel sheets without any detection. I mean, without any defect. Okay. And at present only manual methods are there, so you try to automate the entire system using the machine learning algorithms, so that you can identify the defects in the online during the fabrication itself. Okay. So for this purpose we are using convolutional neural network actually. Right. So what are the research highlights? We are going to detect the defect online itself. Then we are using some methods, AI based methods for feature extraction. Okay. Then classification of the defects is done using CNN, hybrid KNN, SVM, and so on. And we are trying to obtain an optimal accuracy rate. So if you see the results, okay, so these are the various types of steel sheets under processing, and we are identifying the defects. Okay, so this is done online, so you are able to capture the defects and obtain a surface plot based on the defects that is existing on the shield steels. And based on the I mean, during the training process, the accuracy we try to achieve is very high. Okay, maximum amount of accuracy was achieved to detect the defects. Okay, and the defects were also spotted out using this kind of boxes to indicate the defective areas on the steel sheets. So now this is the inference that we have made. We have taken a total number of sample sizes 1256, and for training testing we have taken 126. Then validation another 126 was taken. Then in this 1256, what are the defects? Map cracking, scratches, patches, and surface bits. So each we have taken 314. Okay. And then for testing, slightly lesser number of images were taken, testing and validation. And the efficiency was found out for training, testing, and validation. Okay. So, and we have adapted the feature extraction methods, that is faster RCNN, KFNet model, OCA-FRN model. And we found that in the feature extraction during the training, testing, and validation, this OCA-FRN model was able to give the maximum accuracy for detecting the defects. Then in the classifier, 3 classifiers were proposed: CNN, hybrid KNN, and SVM. And in that, the SVM model, right, it was giving the maximum classification uh, for detecting the defects in the steel sheets. Okay. So this study is introducing a OCA-FRN model for detecting the steel sheets, and actually four different types of defects were analyzed, and also this defects, whatever images you are capturing, that was captured under various lighting conditions. So LED lightings can be used. Normally in factories, you won't, in the steel sheet processing industries, it will be constructed on a huge land area with high ceilings. Okay, so the light distribution patterns will be different. You can use linear luminaries, high daylight, and task lighting, and so on. And you can see this model will help you to also tell which kind of lighting is suitable to detect the flaws for during the manufacturing of steel sheets. So this OCA-FRN model was able to process on low resolution images, okay, to detect the flaws that was available. Okay, so any missed detections and imprecise localization can also be monitored and detected using the OCA-FRN. Okay, so this algorithm performs well with maximum accuracy, thereby detecting the defects on the steel sheet surface. Okay, and as a future direction for this study, you can include some more defects also. Now at present we have taken only four defects, yeah, so we can include lamination, center burst, clings, etc., as an extension of this work. So these are the two applications for automating the industries to make the industry a smart industry. Now I end this presentation. So it is open for the question session. You can ask me any questions. Open to the part.
Participants, if you have any questions, you can unmute yourself and ask. Participants, if you have any questions, you can unmute yourself and ask. Any queries from the participant side?
Even if you have queries, put in the chat box. Yes. Hema ma'am, you can.
Okay, ma'am. Okay. So I don't find this. Okay. Thank you, Sujata ma'am, for your valuable insights on smart systems in industrial automations. And we had a message in the chat box like the pictures of pole defect using camera was nice from the participants. Yeah. So thank you, ma'am. Thank you for sparing your valuable time with us. I request all the participants to turn on your video for your photo session. Jasmine, ma'am. Ma'am, have you taken? Ma'am, you have taken?
Yes, ma'am. Yes.
Okay. Okay. So shall we end the session, ma'am? Okay. Thank you all.